I was going by Mass Mutual, and what I noticed, the guy's cleaning the window, and this is what I saw. They had a piece of wood. They're standing on a piece of wood. Here's the piece of wood. Let's say that piece of wood is, what's an average length for? Maybe 3 meters long. You don't want it to be too long. They'll be saggy in the middle. 3 meters long. Let's assume it's uniform. It has a mass of 20 kilograms. If I was standing on that, I want to make sure that piece is really solid there. It's not a cheap piece of wood. I don't want it to snap. I'm dangling up in the air. There's a person standing here cleaning the window. His mass is 80 kilograms, and he's standing 1 meter away from the edge, from this edge. There's a bucket of water here to clean the windows. And the mass of the water is 25 kilograms. And that water is, let's say, 1 meter from this end. And there were 2 ropes holding this, one pulling up in this direction and one pulling up in that direction. And I have no idea what these forces are. The rope, let's call them force 1 and force 2. And the question, what are the forces? Find F1, F2. So I'm going to do a free body diagram. Here's the board. Since the board is uniform, it has a center of mass in the middle. This is the weight of the board, which is what? Mass times gravity. 20 times 9.8. Is that 196? And if I use this as the 0 mark, that's actually 3 meters from it. Oh, I'm sorry, 1.5. The whole board is 3. 1.5 is smack in the middle. I have the weight of the person right here. And that's the 1 meter. No, it's not to scale here, but the weight of the person is what? 80 times 9.8. 784. I got the weight of the water here, which is 25 times 9.8, and that's 245. And I got this rope here pulling up F1 at the 0 mark where I'm measuring the distance from, and I get F2 pointing upward. These are all the forces on that beam. That's why I saw this morning at 7 o'clock in the morning. Guys cleaning the window. I looked at it, so good, perfect. Perfect topic for today. And the question is, how much tension, the force by the rope, they have to pull up to keep that plank, the person and the bucket of water from falling down. Because if that rope, if you use a cheap string there, is going to snap and they're all going to be tumbling down. So what do we need to keep that person up there? What's that force and what's that force? Here we go. Nothing was moving. This was stationary. It wasn't spinning. It wasn't going up. It wasn't going down. It was just stationary. That tells me we have static equilibrium. We have a balanced system. If we have a static equilibrium, That means if you take all the forces pointing upward, you add them, they should equal all the forces pointing down. Sum of the forces has to be zero. There is no net force. Static equilibrium says the summation of the net force is zero. No net force. Zero force. Which means we have forces, but the result is zero. That means the ones pointing upward canceling the ones pointing down. What is pointing upward? F1 plus F2. What is pointing down? 784 plus 196 plus 245. So F1 plus F2 have to be what? Let's add these numbers. 245 plus 196 plus 784. 1225 Newton. These are newtons, these are newtons. Okay. One equation, two unknown doesn't help me. There is nothing in the x direction. Nothing. So I can't do sum of the forces to the right equals left. There is no right and left here. I have two unknowns. I need a second equation. Now let's take another look at that beam. Was the beam turning? Was it spinning? No. That means zero torque. What does that mean? The net torque has to be zero. You pick any point on that board, anywhere you want to, and you calculate the torque, it should be zero. If you want to make the math easy, a little bit easier, you pick a point where you have an unknown, like this point or that point. So maybe I'll use that point. The torque by F1. F1 times 0. The distance is 0. It's not plus, it's not a minus. F1 is not going to make it spin. It's positive 0, negative 0 is the same thing. But let's get to this one. This one's going to make just that beam. If that's the only force on it, remember that's your pivot point. Is it going to make spin clockwise or counterclockwise? Clockwise. That's a negative. 784 times the distance from here to there, which is 1. Let's get to the second one, the 196. Is that 196 going to make the beam? You only look at that force. You said the other ones are not there. The 196 is going to make it spin clockwise or counterclockwise? Clockwise, that's a negative. 196 times the distance from here to there, which is 1.5. Now we get to the bucket of water. It's going to make it spin clockwise or counterclockwise? Clockwise. 245, and what's that distance? How far is it from the pivot point? Is that a 2 from here? Because only 1 meter from that edge, which means 2 meters from that end. And that's the 3 here. And what about the last one, F2? That's positive because why? F2 is pulling up. Which way is it going to go? Counterclockwise. So it's F2 times the distance, which is 3. The sum of that should be 0. Let's see what that number is. 784 times 1. 196 times 1.5 plus 245 times 2 minus 1568 is equal to 0. 3F2 equals 1568 And what's F2 equal to? 522.7. So the tension in this cable on that end is going to be 522.7 Newton. That's how much the force, the pulling force on that end. Now, what about F1? You go back to this equation now. F1 plus 522.7 is equal to 122.5. Can you get F1? It is 702.3. So F1, the force here is larger than the force right there. Why? Because the person's standing right next to it. The closer that person to this, the more pushing on that one. The farther you are, the less on this, the more on that one. Now let's try another one. Today the weather is going to be nice and the rest of the week is going to be beautiful, just like what we had last week. So you might decide to go to the pool swimming there. And let's say you have a pool here and you got a diving board right here. Usually the diving board has a support right here, a little piece of support, this concrete here. And you also have another one right here with the screw on top of it, a little bolt on top of it. So the person stands on the tip of the diving board here. Now, if there's nothing holding this piece will pop up there, goes up in the air. We're not sure what these forces is going up, down, which way. You can really make an assumption. You go, I have no idea what's going to happen. I'm going to assume this force is going to be pushing up in this direction, this will be pushing up. I couldn't tell you. This might be down. My gut feeling, that's up, this is down, but I might be wrong. But who cares? You make an assumption, if the value comes out negative, it's your direction is wrong. It should be pushing down. Let's give the person a mass, how heavy the person, what do you want it? And how long the diving board? $90 kilograms. This is a 5-meter long diving board. Five-meter diving board. We're going to neglect the mass for the diving board. Neglect the mass of the diving board. And let's assume the distance from this to here is 1.5 meter. I'm neglecting the mass of the diving board. I can really put it in, it's not a big deal. If you want to put it in, we can put it in. Doesn't change anything. So this is my diving board. If I use this as the 0 mark there, I have F2 pointing upward. I had F1 pointing upward, and that distance is 1.5, and I got the weight of the person pushing down, which is 90 times 9.8, and that's at 5 meters away. Ninety times 9.8. It's 882 here. Again, you're standing on that diving board, nothing is moving. Nothing happens till you press your feet down, then you go up in the air. So if you're standing on it, we have static equilibrium. The thing is not spinning, thing is not moving up or down, which means if you take all the forces pointing upward, have to equal all the forces pointing down. There is no left and right here. Upward is F1 plus F2. Since I neglect the mass of the board, that's a 0 mass. So the only way down is the 882. That's it. Second one, the net torque is 0. And you can pick any point for the net torque, any point you want to. I can pick this point, I can pick this point, I can pick anything. If I pick a point that's not this or this, the second equation will have F1, F2 in it. I gotta solve 2 equations by 2 unknowns. But if I pick one of these, the second equation is only gonna have 1 unknown and makes the math easier. So if math is not an issue for me, it really doesn't matter which one I pick. But if math, I'm not good with solving 2 equations by 2 unknowns, then you pick one of these points. If I pick this point as a pivot point, as I said, I can use any point. If I pick this or this, the second equation will only have 1 unknown in it, and I can solve it. So let's look at this one. First, F1 will have 0 torque because notice the force goes right through that pivot point. So R is 0. There is no distance between the force and R. It goes right directly through it. But what about that weight there? That weight's going to make this spin, looks like clockwise. If it's clockwise, that's a negative torque, and it's the value of the force, 882, times the distance from here to here. And what's the distance from here to here? 2.5, yes. And what about this one? F2 is going to make it spin which way? Clockwise? Clockwise. That's a negative torque also. F2 times the distance from here to there, which is what? 1.5. Remember I said usually they have a bolt on that end to hold this from flipping. Because if that's just a piece of wood like this, you lay it like this, and you stand on it, what happened to the back piece? Start to lift. The only way not to lift it if you put weight down on it. So that force really should be pushing down to keep it from lifting up. So that should be pointing down, but I pretend I don't know that, and I made it pointing upward. The math is going to tell me that value is negative, which means I'm wrong. It should be pointing down, that force, to keep that from going up there in the air. So we do the math here.
I think that should be 3.5.
Is it 3.5?
Yep.
5 minus 1.5? Yep. Thank you. 3.5. So So 882 times 3.5, that's a negative 3087 minus 1.5 F2 is equal to 0. So F2 is going to be what? Negative? It's negative 2058 Newton. Negative, which means, sorry, it should be pointing down, not up. That's what the minus sign tells me. You don't have to go back and redo it. Now you know it's pointing down. Now to find what F of 1, there's a little support, there's a beam right there, you a piece of metal there, or a block of concrete here to hold it, make it a spring. So there'll be F1 plus F2. F2 is what? Negative 2058 equals 882. When you bring this to this side, it becomes a plus. And that's 2940 Newton. So what we found out actually right now, that my picture, the way I drew it, it's a little bit off there. What's going to happen is not what I thought is going to happen, or I didn't think about it. I have the weight of the person down, which is 882. This force, yes, it is upward, and this is 2940, but this force is going to be pushing down, not up there, pushing down here of the value of 2058. And notice if I take this, add it to that, they're the ones pointing down, should equal to the one pointing upward. Now I've been making every problem beautiful there, everything on the y-axis. Well, that's not always the case. So let's make somewhere, these are not 90, it's like straight up and down, on an angle. I'll do a couple examples like that. Remember that sign, the guy is selling honey, whatever it is? Let's go back to that one. We'll put this beam in the ground. So we have there's a screw here holding it, or a nut there, a hole with a nut holding it. So this beam is free to move, can go up and down. The mass of this rod is 3 kilograms. Can't be, let's make it bigger, 5. Uniform beam, 1 meter long. Now on this end, the guy is selling honey, we said. So there's a sign here, honey for sale. He has this sign made, it says honey for sale. Well, that sign is going to have a weight on it, a mass. So the mass of this sign, let's say it's 3 kilograms. Made out of wood, so it's not a heavy sign. And to keep everything from falling, this person decided to take a rope, but not to the top here. He attached the rope somewhere here. Let's say this is actually the 80 centimeters, 0.8 meter here, the distance. He put a rope there to hold it down. And the rope was pulling in that direction to keep that sign from falling down. Let's give it an angle here. What angle should we use? What do you want to use for an angle? Pick a number. Okay, I'm in no rush. I'll wait till 12 o'clock. Choose a number. 37. The question is, there's a force here. Do we know that's up or down? In and out? If you think about that, the fact the rope is pulling down, pulling this way on it, if there was nothing here, if I didn't have that beam, this will go into the wall like this, will slide in. So the reason it didn't slide in, it must be a force pushing at it from this direction. And when you attach that beam here, why didn't it fall down? If I don't put like the screw in this hole here, if I just go like this and I attach a weight to it, it's going to go up and comes out of the hole. So why didn't it come out of the hole there? Maybe somebody was pushing down on it here. Maybe there's a force pushing down right there called Fy. And I don't know the direction of them because I'm adding more weight. It could be going upward. But the math will let me know. So if I look at that beam, this beam right here, and I do a free body diagram, this is what I see. We have the weight of the sign. The sign's 3 kilograms. 3 kilograms. What's 3 times 9.8? 29.4. This is the 1 meter. If I use this point here as to measure everything from it, this is the 0 distance. I also have the weight of this beam itself. Since it's uniform, it's going to be smack in the middle here. 5 times 9.8, that's 49 Newton. And this is a 0.5 meters. Uniform beam. So the center should be in the middle. I have the tension here in the cable pulling upward, T, at 37-degree angle. And this is 0.8 meters. I have this force, we'll call it F, in the X direction. And I get this force down, I drew it down, F in the Y direction. These are all the forces that I have. This is my free body diagram. What I don't like about this is that T has an angle. It's not on a 90-degree angle. So let me take that T, replace it with a component in this direction, a component in that direction. So I will have 2 components to that. This is the 29.4 at 1. This is the 49 at 0.5. This is Fy. And this is Fx. This is the 0 mark. And now I'm going to take that 0.8 meter right here. And I'm going to replace the T with 2 values. Notice to go from here to here, you have to go to the left, then go up. Left and up, which means you have a component to the left and a component up. And if I know what these values are, I can start solving the problem. The value to the left is this one. That's the adjacent to this angle. So this is t cosine 37, and this is t sine 37. T cosine and t sine. The y value, that's this one, that's the side opposite to this angle, that's why it's the sine. This one is the adjacent to that angle, that's the cosine. And we're assuming that sine is staying there, it's not moving. So we have static equilibrium, which means what? Three things here, because we have x and y. First one, this is if you take all the forces, the net forces in the x direction is equal to 0 in the x direction, which means all the forces pointing to the right, if you add them, they should equal all the forces pointing to the left. Because if you have more in one direction, the thing will move horizontally. What do we have pointing to the right? F of x. What do we have pointing to the left? T cosine 37. That's one equation. Two unknowns, t and f of x. We also have the net forces in the y direction is 0. What does that mean? If you take all the forces pointing upward, should equal all the forces pointing down. What is pointing upward? I see t sine 37. Anything else pointing upward? No. What is pointing down? Fy plus the 49 plus the 29.4. So t sine 37 equals Fy plus is 78.4. And that's my second equation. Now, how many unknowns do you see in these two equations by, is it 3 unknowns? That's a 2 equation by 3 unknowns. We can't solve that. None of us can solve it and get a number. I need one thing. Something has to be given. Well, nothing is given. So the last piece, was this beam spinning? Was it rotating? That means sum of the torque. If you pick a point on that, the net torque should be 0. And again, you always want to pick a point where you have an unknown in it to make the math easy, but it really doesn't matter which one. So if I pick that point for the torque, this one has 0 torque, this one has 0 torque. Because the distance from the force to the point is what? Is 0. This one has 0 torque because it goes through the point. There is no perpendicular distance to that one. So the only torque is this, this, and that. So I'm going to pick that point. The torque done by this is going to make it spin which way? Clockwise, and we use negative. This one, that's also clockwise, that's a negative. And this one counterclockwise, that's positive. T sine 37 times the distance, which is 0.8. All of that should equal to 0. All of it. I'll do the math. Negative 49 times 0.5 minus 29.4. Oh, I forgot to turn it on. Negative 53.9 plus t. What's sine 37 times 0.8? Sine of 37 times 0.8. That's 0.481. What's that noise? Can we get what t is? And I get t to be 112 Newton. 111.95. So the tension in my cable, 112 Newton. If I know the tension, can I find f of x and f of y? Go back to these two equations. Now f of x equals the tension, which is 112 times cosine 37. One 112 times cosine of 37, 89.4. And it's positive, that means my assumption is going to be in that direction is correct. If I get a negative, so you're wrong, it should be going backward. I hope Fy is negative. Just to show you, it doesn't matter what assumption you make. 112 times sine 37 equals Fy plus 78.4. 112 sine of 37, 67.4 equals Fy plus 78.4. Can I solve for Fy? Bring it to this side. It becomes a negative. It's negative 11 roughly. So that's, you know the assumption I made that Fy is going to be pushing down? They're going, you're wrong here, it's going to be going upward. Because of that cable, the weight and all the stuff, this is not going to be really pushing down, it's going to be going upward. But we found all the pieces that we need to find. One more example with these. Here we go. I want to make sure this video has all the stuff on it. Let's say you're painting. This is a room inside your house, and you got your ladder here. You're going to paint the ceiling of the house or the wall. We have a ladder there. The height here is 3.8 meters. So we have a person standing on the ladder. The person is right here. that person is not at the top of the ladder. So somewhere here, we'll get to that later, we'll see how far that distance. But the mass of the person, 85 kilogram. Now, let's assume the floor here is really rough and you want the floor to be rough. Because if the floor is not rough, what's going to happen? That ladder will slide back. If this like marble floor, the minute you start to climb, you'll see that ladder goes whoosh from under you. So if it's rough, that means the ladder is pulling in opposite direction to keep it from sliding. So there's a force in this direction. We'll call it F1. I don't know, I'll give it some numbers. I haven't. Or F friction, whatever you want to call it. There's also the ground. There's a weight of the ladder and the person, so there's the ground pushing up there too, of F2. I can call it P for push, R for friction, whatever. Let's assume the wall this side is really smooth. Because if it's not smooth, there's a friction force. This wants to go back, the friction force is upward. But if it's smooth, the only force on that will be in this direction. Because if I make it friction, there'll be 4 forces. Now we got a lot of work to do with math. So this eliminates, makes it 3 equations by 3 unknowns instead of 4 equations by 4 unknowns. So I'm making this wall frictionless, which means I don't have anything in this direction. If it wasn't frictionless, again, this one wants to slide down. The reason it's not sliding, there's a friction force be pointing upward. So I don't have to deal with that here. We gave you the mass. How about the ladder itself? Should we give the ladder some weight there, mass there? We can say lightweight ladder, we can give it a mass. It really doesn't matter. Let's give it a mass. The mass of the, I don't care how you say lightweight, it still has a mass. Even the fiberglass ones. So the mass of the ladder is 10 kilogram, uniform. And the person, the distance actually is 0.7 meter. By giving the mass, I don't know if I have to give you now something else, angle. I just added the mass here. The problem was lightweight ladder. We need, like the mass, we know that distance will be down halfway here. So you just gotta figure that, somewhere here, gotta figure out what that distance is. Might have, you know what, let's go a lightweight ladder. Because otherwise I have to give you something else in the problem. I have to give you an angle. I don't want to give you the angle. You know? So I'm going to make the mass of the ladder 0. Instead of 10, it's 0. So it doesn't really have any mass. The ladder is lightweight. Special ladder has no mass. You can pick it up with one finger. A fly can pick it up. There's no mass for the ladder. Otherwise I have to tell you what that height of the person is. And the question, find F1, F2, F3. neglect the weight of the ladder. They're neglected. Neglect the weight of the ladder. So 0 kilogram for the ladder. So if I just drew the ladder here, free body diagram, there's my ladder. These are my forces. F2, F1. There is no weight for the ladder, but we have a weight of the person down. Which is 85 times 9.8. 833. And we know that distance is 0.7 meters. We also have this force in this direction, pushing, F3. We know this distance, 3.8 meters. So those are my forces. And I lucked out everything either in the X direction or in the Y direction. Now we are assuming the ladder is not moving. It's not sliding, it's not spinning, just laying on that wall there. So if we look, some of the forces in the X direction, the net force in the X direction is 0, which means all the forces pointing to the right should equal all the forces pointing to the left. What do we have pointing to the right? F1. What do we have pointing to the left? F3. This has to equal to that. Oh, that's actually not bad. By neglecting the weight of the ladder, well, even if we didn't neglect it, I just need to give you the angle or something. In the Y direction, the net force in the Y direction should also be 0. That means all the forces pointing upward, if you add them, they should equal all the forces pointing down. What do we have pointing upward? F2. What do we have pointing down? 833. So if this is a homework question, we got one part right. We got a third of a point. We got that force. Find F1, F2, F3. We found F2. I still need F1 and F3. So I found 1, but I'm still missing F3 and F1. Since nothing's spinning, the net torque, sum of the torque, or the net, is 0. And I'll pick that point because it has two unknowns in it for torque. That's a good spot. Anytime I have a point with a lot of unknowns, I tend to choose that to make my math easier. But any point on that ladder, you could have picked this point, you could have picked that point, that point, that point, this point, that point. It doesn't matter which point. Since I picked that point, this and this are gone because notice they go through the pivot point. There's no torque by them. They don't make it spin. Only this one and that one will make it spin. This one make it spin which way? Clockwise. That's a negative torque. and is the value of the force times the perpendicular distance to that pivot point. The value of that force is 833, and the distance from here to here is 0.7. Now let's look at F3. F3 is going to make it stop pulling, and it's going to make it spin counterclockwise. That's a positive torque, and the value of that force, which is F3, times the distance that's perpendicular to that pivot point. Here's the distance perpendicular to that pivot point. The force in this direction, so I need to know what that distance is. What's the distance from here to there? 3.8. How many unknowns do you see there? One. 3.8 F3 is equal to, becomes a plus when you move it to the other side, 833 times 0.7, 583.1. What's F3 equal to? 153.4. And we know F1 is equal to F3. F1 equals 153.4. So I answer all three questions, 1, 2, and 3.